Electric charge and electric field. Next up, we have the concept of uniform electric field. A uniform electric field is one that has constant magnitude and direction, not only with respect to time, but also with respect to position. No matter where or when you look, the electric field will have the same magnitude and direction. The electric field produced by a single charge, for example, is constant only in terms of time. 1 second, 2 second, 3 second, the electric field produced by a single charge remains the same. But when you look at different locations in space, you will find different values of the magnitude and different orientation of the direction for the electric field. In that regard, the electric field produced by a single charge is not uniform electric field. Again, for uniform electric field, the magnitude has to be constant, the same for direction, not only with respect to time, but also with respect to position. No matter where you look in the space inside the electric field will have the same magnitude and direction. One example of a uniform electric field is the electric field produced by two charged plates, one positive, the other one negative. Electric field will head away from the positive plate and head towards the negative plate. And the closer the two plates are, the more uniform the electric field between them. Wherever you look inside or in between the two plates, the electric field will have only one direction and one magnitude. And this is constant with respect to time. You have uniform electric field. It has constant magnitude and direction, no matter where you look inside the plate and no matter what time it is. Uniform electric field. For a uniform electric field, E is constant and it's still equal to F over Q naught. Transferring Q naught to the other side, F is equal to Q naught E. Q naught is constant, electric field is constant, which means the force that the electric field will apply is also constant. And since the force is constant, we can use the equation from second law of motion, special case, F is equal to ma. Force applied by a uniform electric field. So let's have one example. Sample problem number 3. Determine the electric field magnitude needed to cancel out the gravitational force on an electron traveling in a uniform electric field. The particle or the object is an electron. We know the mass of the electron to be 9.109 times 10 to the negative 31 kilograms. And the electron charge, Q naught is equal to QE, charge of the electron, negative 1.602 times 10 to the negative 19 coulomb. We are looking for the magnitude of the uniform electric field that the electron is traveling in. We are looking for E. Now, the problem tells us that the uniform electric field will apply force on the electron, and this force should be enough to cancel out the gravitational force or the weight of the electron. The force applied by a uniform electric field is constant and it's equal to F is equal to Q naught E. Magnitude of the electrostatic force or electric force, F is equal to Q naught E, where Q naught is in absolute value sign to get rid of any negative signs because we're talking about magnitude of the force and magnitude should always be positive. Q naught is equal to QE, so let's replace Q naught with QE. F is equal to QE E. Now, there are two forces acting on the electron, the weight of the electron and the force applied by the uniform electric field. So, F net is equal to weight plus Fe. And the problem tells us that the electric force applied by the uniform electric field will cancel out the gravitational force. So F net is equal to 0. Weight is vertical. For Fe to cancel out the weight, Fe should also be vertical. Particularly if F net is to be equal to 0, meaning all of Fe is cancelling out the weight. So Fe should also be vertical, meaning all the vectors in the equation are vertical. No x component, we only have the y component. So going directly to the y component of 0 is 0. Y component of the weight is vertically downward, so negative w. And y component of Fe, we are looking for Fe, so we simply use Fe in the equation. And the equation will tell us that Fe is just equal to the weight magnitude of the electron. And Fe is just equal to QEE. Isolating E, we know M, we know G, 9.8 meters per second squared, acceleration due to gravity. And we know QE. QE is negative, but it's inside absolute value, so we get rid of the negative sign. Completo. We are able to calculate the magnitude of the uniform electric field. E is equal to 5.572 times 10 to the negative 11 Newton per Coulomb. And that's it for now. That's it for our discussion on uniform electric field. We'll continue our discussion on electric charge and electric field in the next video. In the next video, we'll take a look at the concept of the electric potential. So again, that's it for now. And thank you for watching.